Hello, everyone. This is a look at Lab 8. Um, we've uh, got several parts of this that we want to look at. And what we're doing is applying some of the things that we talked about in earlier lectures to specific situations, uh, basically to investigate how motors and how generators work. All right, and you'll notice that there's uh, several there's three parts and there's several questions for each part, and so this is the point of this is uh, to go over the lab in a bit so you can see how to work things. All right, and so for the first part, this is something we'd have expected you to do in the lab normally. This is straight out of the old lab. The idea is that there's a current, and that current is running through this magnetic field. That current should feel a force. And so this is a task of doing the right hand rule that we discussed earlier. So if you have been paying attention, my videos are up on YouTube, and Dr. Houston's videos are up on YouTube, and I think I've posted all the links to D2L, so you can go look at these. And a lot of what we're talking about here, I've covered in a theoretical sense. The idea is that you're supposed to go through and investigate that it makes sense. All right. So we're going to look at these apps for a little bit. This is a, a simulation of what we would have done in the lab: is have a magnetic field and have a current flowing through this magnetic field. And so there's a current here. We can turn on the current. We can change the orientation of the field. Uh, and we can ask what's going on. Right? And so what we want to do is use the right hand rule to predict what's going on. And in this case, when I have the current flowing, the current is moving sort of toward the left, toward out of the screen. And you would put your thumb in that direction, and your fingers would go down the screen in the direction of the field. Right? So the current is going this way, that's your thumb, and the field is up and down, that's your fingers. And then your force, the way you're pushing, would be to the left. If we reverse the current, we change the direction the current's going, we should change the direction of the force, and that's what happens. And if we change the field, that should change things as well. Right? So the idea is that you can go through and think about what's going on in the thing that we've laid out here for you to do is draw the field lines that you expect, right? What field lines do you see out of the north pole of a magnet? Which ones do you see out of a south pole? And then using the current and the field lines, do the right hand rule to figure out the direction of the force. And so for the first one, you can look at this, and you're basically holding your hand up to the screen. Your thumb is the current going to the right. Your fingers are going up. That force will be out of the screen. Remember, this is bolded in the lab. Circle with a dot is out of the page. Circle with a cross is into the page. So you go through and you fill those in, and you can kind of get an idea from the app what's going to happen here. So the second part is starting to get to what happens with a motor. Right? And so here we have this coil, which we would have built in the lab, or had you think about at least. And the idea is that the current goes around. So if we start here, the current's clearly marked to the right. And as we go around, it turns down, and then it goes up behind this other loop, goes up, and then it goes to the left, and then back down, and to the right, and out. So, again, follow the little cursor on the screen. It's going in a circle, in a loop. So based on your answers to the previous part, you can tell what's happening to the what the force is on the current at the bottom of the loop, and that the force is different on the top of the loop. And what this is going to do is cause the loop to try to rotate. So you can also ask what's happening on the sides. The current's parallel to the field. That should tell you something about the force. Right? Remember, your force is Q times V times B times sine phi, or I times L times B times sine phi. So ask what is sine of phi for each of these cases. And particularly the up and down ones, you know what that is and you know what the force should be. So the loop's going to try to rotate, and we're going to get to the point where the loop has rotated halfway around, 180 degrees. Now, the current at the top of the loop changed direction, and the current at the bottom changed direction. You now have it goes around the loop in the opposite direction, clockwise instead of counterclockwise. And so you're going to ask what the forces are there. Now, we lead to a conclusion. This third question here is that motors turn around in the same direction. What you should see is that this motor, as described, doesn't work. It oscillates. It goes between the two pictured states, between the top picture and the bottom picture, without making a complete rotation. The forces are always going to oscillate like this. And so we ask you a question. What do you need to do to make it always turn the same direction? Now, you don't need the force to be constant. One solution, and that's what the video following up is going to talk about, is only have one set of forces, is have the top picture happen, and when you get to the state where the bottom picture happens, have there be no force. Don't pass a current. It doesn't have a force, but it'll keep rotating. It'll have inertia, so it'll coast onwards until it gets back to this picture, and then it'll have force again. Another option is to always have the current flow in one direction. The trick is whenever it rotates around, you have the current flop directions as well. So having an alternating current going through here and having the motor spin at the same rate the current changes will do this. So there's a few different ways of solving this problem, but we want you to go through, watch this other video. I'm not going to play it because it's got some annoying music, but you don't need it. There's no text, there's no lecture to it. Just watch the video, watch the building of it. You would have built this in a lab, and we would have let you do it on your own and just answered questions for you. All right. So the third part is about generations and about inducing current in a coil. And so what's here is when you use this app, you have, and this has to load for a minute, obviously. I'll come back. You have a voltage probe hooked up to this coil, and you have a light hooked up to it. And you can turn on whether the field lines are on. Let's see if that's there. Yeah. All right. So we can turn the field lines on, and you have a magnet. And you can do things like put the magnet into the coil, take the magnet out of the coil, pass it through completely. You can't put it through sideways, right? It understands that it's a real thing. You can put it in and leave it there, and you can change the direction of the magnet. You can change the direction of the field, cause it to alternate. And you can also have two coils. You can try what happens if you have more turns or less turns. So with this lab, what we want you to do is carefully go through these questions. All right, and basically, we're kind of giving you some of it. Is number 2 is answered here, but answer the questions as they go on, and note that as you put in the magnet or take out the magnet, there will be a change in this voltage reading. And it's qualitative. What we want is it positive or is it negative? Is it big and positive or big and negative or small and positive or small and negative? All right, is we we want you to pay attention. Basically, grab the thing and move it while you're watching the light and while you're watching the meter. All right, so be very careful as you're doing this, and answer the questions carefully. And what you'll get to is sort of the things that I'm getting to in the lecture is we're inducing current in this coil, and there's a question of which way is the current induced. So this is the Faraday's law and the Lenz's law. So if you look at those videos, that'll help a bit. Right. So hopefully that's sufficient. If you've got questions about this, please feel free to email. I don't think I've missed anything. This is a new lab for me, but I think this should be okay. Please, yeah, feel free to email if you need.